Okay. Okay, so my name is Nobu, and I'm going to talk wireless synchronization in data center and beyond. And so, well, we already gave a nice talk about using the LoRa board, and I'm going to talk about the 900 megahertz FSK board, and also talk about the YY with the Wi-Fi board today. So, today I'm going to sort of the problem to solve in data center is that we want to solve the network congestion. And what I mean by that is when data network becomes congested and overloaded with data traffic, which slows down the speed of data transfer and can cause data loss. And we will solve this problem with the synchronization. That's the big picture. And we want to bring in the wireless synchronization into this into a data center, and this is the some of the use case in data center, which is we usually bring in the GNSS or GPS receiver signal with wire to the servers that have time cards, and then but we want to get rid of these wires mainly because like urban data center, especially that's typical in Japan, that data center, they don't own the building. So they often cannot run the cable from their room to the ceiling. So in this case, this wireless synchronization will definitely help. So what we do with wireless synchronization is basically same as the PTP protocol, T1, T2, T3, T4. We have the transmission time, reception time, and then the other way, the transmission time and the reception time. But there is actually big difference or big addition to this PTP, which is like a White Rabbit. We do the synchronization as well, which is to say we record the transmitted phase and received phase, and we do phi 1, phi 2, phi 3, phi 4. And by looking at these phase information only, we can get the transmission, the variation of propagation delay, and also variation of the clock delay, clock itself. And by feeding back this variation of clock information back to the oscillator for the follower, we can actually phase lock the leader clock and the follower clock through the wireless channel. So this is the sort of essence of what we do with YY. The important thing is we can even phase lock, and then after that, after the synchronization is done, we can do the synchronization. So this is the movie demo for the synchronization, and you see that where it's not phase locked, the frequency for 10 megahertz for two oscillators are not aligned. But pressing the button, it feeds back to the signal. Let me say, to the follower follows the phase of the leader clock. And so we implemented this to the time card. So time card can take, like we mentioned, can take two GNSS daughter board, and like we mentioned, the idea is we can use one of the GNSS receiver port replacing with the YY. So this YY daughter board can sort of pretend like a GNSS module. It can provide 1 PPS, 10 megahertz, and time of day to the time card. So by replacing this and having the leader module next to the GNSS receiver, we can make this wireless connection here. And we demonstrated that over 10 days, this system can synchronize within the 12 nanosecond peak to peak. And but this 10 YY part is actually good to so YY connection synchronization is good to nanosecond over 10 days, and aligning or disciplining the YY reader clock to the external GNSS clock part has more noise. So this is the talk. What I was talking was inside of the data center, and now I'm going to talk about the beyond the data center. So from the data center, probably the easiest way to reach to the user is maybe through the 5G radio unit. But what I want to emphasize is in order to reach to user, we definitely need wireless synchronization. Otherwise, you need to be wired all the time. So for that purpose, the Julian, under the OCP collaboration, have developed several boards. And so these two top ones were developed by NICT, but the two bottom ones, I'm sorry, not this, the 2.4 gigahertz OFDM and the LoRa board, they are developed by the OCP collaboration. And so I'm sorry, arrow isn't pointing right, but this is 900 megahertz FSK board, and 2.4 gigahertz Wi-Fi OFDM board was developed by Julian, and this 900 megahertz LoRa board is what we were just talked about. And this board was developed by Julian, and it's open sourced at the GitHub. And so we took Julian's board, and we demonstrated we can do YY with this Wi-Fi board. And the nice thing about Wi-Fi chipset is that in Wi-Fi board, they already have the so-called channel state information. And that is really the measurement of the amplitude and phase of the received signal for each channel. So we use one of those signals to do the YY and monitor the clock deviation, and compared it with the DMTD phase comparison gadget, test equipment here, and both of them are basically measuring the same thing. And so, and also about the space-time synchronization. So this is sort of the motivation of we wanted to apply for the Wi-Fi, and of course, time synchronization is the basis of everything. But if you are synchronized, you can actually also measure the motion. And so this video is kind of old. It was taken like 2015. But Satoshi, he's here. Satoshi made this demo using the iPhone. And in this case, it was using BLE beacon to monitor the position with the 3 receivers that are synchronized with one another. So let me run this. So the position of the sorry, let me try again. So position of the iPhone is displayed on the TV screen, and as he moves around, you can monitor it in real time. So please imagine that all the access points for the Wi-Fi is being synchronized. Then actually you can monitor the position of all the cell phones, which brings another private issue. But I think we need to sort of start discussing and implementing about this technology. So the call to action is, right here, and I want to emphasize that this board, Wi-Fi board, is open sourced at GitHub, and also my talk is also on the OCP TAP seminar page. Thank you.
Thank you, Nobu. So let's open the floor for questions.
So is YY point to point, or could it be point to multi-point? Could you do 100,000 servers in a data center, for example?
Yeah, thanks a lot for the question. So the answer is yes, it is point to point, or it's actually you can do YY comparison with mesh network. And actually, it has since it's the antenna it's sort of wireless communication is broadcast, so it has sort of scaling merit in a sense. Say you have 10 modules, then each module transmitting one signal, so it's like 10 transmissions. Then within the 10 mesh network, there are 10 times 9 divided by 2, so 45 peer-to-peer connections. And all those 45 peer-to-peer comparisons are done by just each person transmits once. So, I mean, but in order to reach like hundred thousand of servers, we need, I think, so the reason I put this phase 1 and phase 2 is, phase 1 is by doing the mesh network time comparison with two-way method. It's good because you can trace with each clock time, but in order to supply to the 100,000 servers, I think we need to go to the GNSS type of way that it's only one way, therefore it's not traceable, but you can supply to like an infinite number of servers. So the phase 2 is sort of what I guess we want to develop in the next step. Thanks for the question.
Thank you.
I can ask another question. So when you go to the phase 2, that will come with a degradation, I'm assuming, right? Because you're going to have a one-way, right?
That's right. And you cannot trace it. You cannot measure how off you are, but it's basically same as GNSS.
All right. Any more questions? If not, we'll give you a head start, exactly 2-minute head start for lunch. So thank you, everyone.
Thank you.